average rate of change. Average rate of change. And we had an example, something like this. We had a table, I think, and we had x here and the value there. We might have x equals 0, 1, 2, 3, 4, and we had a 3, 5, 9, 12, let's see, 7, 7. Okay, so I just made that up. But if we graph that, we have 1, 2, 3, 4. Right? And we have 0. That. And so we have 0, 3. Like that. And we have 1, 5. Like that. And we have 2, 9. Like that. And we have 3, 7. Like that. And we have 4, 7 like that. Okay? So this is a table. This is a picture of the table. And I can ask, first of all, does this represent a function or not? Does that represent a function or not? So what you can look at this, and what's the main qualification that we need to satisfy in order for it to be a function? The main qualification is that you have the domain, you have the range, you have points in the domain, get mapped to points in the range. This is half, and here's a point in the, right? So, like, for example, we have 0 gets mapped to what? 3. And we have, for example, 1 gets mapped to what? 5, and so on, right? Okay, so the main thing is that you don't have this, like that. So you have one thing being mapped to 2. That's the thing that you have to avoid, to call it a function. Now this is called a relation in mathematics, so it's not like this is not useful, just that it's not called a function. Okay, and so a function means you don't have one thing going to 2. That's just the rule, the definition. I don't know why I have speculation about why, they work with functions and not usually relations. Because usually, like, think about it, if you have you want to give a function that, suppose we have a box, a steel box, and we have a flame. How do you draw a flame? Like that, right, with a little candle. And you have, so as you increase the temperature, the pressure will increase, right? Right? You have gas inside. So if you do F of T for the temperature, the pressure is related to that, right? And I guess they don't want to think about situations where you can have one temperature going to 2 different pressures. They want it to be more, less fuzzy than that, right? So they focus on situations where you don't get that. Okay, maybe that's why. Okay, so anyway, we don't want this. We don't want one temperature going to 2 pressures. Okay, so I can ask you then, is this a function or not? I'm just getting you involved in the problem. It's not really what we're talking about. It's not what I want to talk about. But So, so is it a function or not? So somebody said no, but it is a function. But I think the reason they said no is because there's a 7 and a 7 here. But that's not a problem. Two things going to 1 is a problem. But let's say here's 2. If we had that, that's not a problem. I mean, it's allowed. We don't rule that out. We can still call that a function. Okay, so you're allowed to have 2 things going to 1. You're not allowed to have 1 thing going to 2. It's just arbitrary. That's the definition. Okay, so here, I think maybe someone was thinking, well, 3 goes to 7 and 4 goes to 7. That's not allowed. No, that's not what's not allowed. What's not allowed is 3 goes to 7 and 3 goes to 5. That's not allowed. Okay? So that's called the vertical line test. That's why the vertical line test works. Because if you draw a vertical line here, you get 3 goes to this and this. So that's not okay. Okay, so this is a function. Okay? All right, but that's not what we're here to talk about. What we're here to talk about is the average rate of change. So that means, that's just the slope. It just means the slope. So if I ask you, what's the slope between here and here, between 0 and 1? So I don't think anybody has any trouble calculating that. The slope means the change in y over the change in x, right? And so from 0 to 1, the change in x, 0 to 1, is 1 minus 0. And the change in y is 5 minus 3. So it's just, the slope is 2, right? But it's a little bit, the average rate of change allows us to talk about, then how we can also say, well, what's the average rate of change between 0 and 2? Okay, so what is that? So if we go between 0, so this was from say 0 and 1. How about 0 and 2? So what about that? So then, still assume simple, but now we're going what? So we're going, so let's say delta x, the bottom, is the 2 minus 0, right? And the top is what? 9 minus 3. So that's different, right? That's not the same as the other one, right? So the average rate of change is different in between different points, right? And that just means that, you know, if you look at the slope from here to here, you get one thing, but if you look at the slope, well, it doesn't look so good here, but it looks like it's almost the same, but I don't think it is the same. Maybe I drew it wrong. 0 and 1, 0 and 2. Anyway, you see? And how about between 0 and 4? So if we do that, what do we got? 0 and 4. Now what? We get what? So 4 minus 0. And on the top we get 7 minus 3. So that's the slope what? From here to there. Okay? So we're talking about that situation. Okay? Those are called the different average rates of change. The average rate of change between 0 and 4. The average rate of change between 0 and 3. The average rate of change between 1 and 4. Okay? All those things are called the average rate of change. Okay? So the average rate of change means just delta y over delta x. Okay, so we have that concept. And then, so why we bring that up? Because we want to have, I want to be able to, let's take an example to make this it's a little bit interesting. So calculus comes from physics originally. So let's take a physics example because that's kind of the one that probably fits most neatly. So let's just try that. So let's take, suppose we're standing on the top of a building, and we're standing up here, and we take a drop it. Okay? And we have so we can call the distance that it falls, we'll call that S. They usually call it S, not D, because D is for something else. So this distance that the ball is falling is called S. Okay? And then we have also, so that's the distance. Distance traveled, or distance falling. Okay, S. And then we also have T, and that's the time. Might be in seconds. And this might be in meters. Okay? So I think that it's completely obvious that the distance depends on the time. Right? As the time increases, it's falling further, right? Obviously, right? When you drop the ball, after 1 second it's here, after 2 seconds it's somewhere else. So obviously the distance, S, is a function of T, right? Okay. So let's be Isaac Newton. Remember, Isaac Newton was in 1500s, I think? About 1500s, about 500 years ago, trying to figure out the relationship between those two things. So how are we going to do that? How are we going to figure out, what do I mean by the relationship? I mean, we said that there is a relationship here, but we don't have the relationship. We don't have what it is. So what I mean is it equal to like 2 times t, or is it equal to like 3 times t, or is it equal to 3t cubed minus t squared plus 1, you know? What is it? Right? Let's be Isaac Newton. How are we going to figure it out? So he's saying, oh, I think there's some relationship between these two things. What, you know, but what is it? Well, how do we do that? There's only one way to do it, and that's to measure, right? To do an experiment. How else are you going to do it? Right? You can't just dream up the answer, I don't think. So you have to measure. You have to start dropping balls. I guess, I think that's right. So we could do that, right? We could start dropping the ball. So suppose we're here, and we drop the ball, and like we have someone here standing in this window, and someone here standing at this window, and someone here standing at this window, and someone here, right? So, you know, we say, okay, when you see the ball, you know, look at the clock. You know, we're going to synchronize our clocks. When you see the ball, tell me record the time, right? So we could do that, right? So then we would get a table, right? So we'd say, this is t, and this is f of t. T, which is s, right, the distance. So we say, okay, so I know that, you know, each one of these is a certain distance, right? That's obvious, right? This is like, 10 meters, and this is another 20 meters, and this is 30 meters, and this is 40, or maybe this is 50 and 100 and 150 and so on, whatever it is. Okay, so we'll have, this is like, you know, let's say 50 meters, maybe that's too big, but 100 meters, 150 meters, 200 meters, and so on. And then they tell me, oh, the time was, 1 second to get there, and it was 3 seconds to get there, and it was 1 second to get there. Does that make sense? No, right? That's ridiculous, right? It couldn't be 1 second to get here, and then only, no, that doesn't make sense, right? So it's 5 seconds to get here, and it's 9 seconds to get here, whatever, right? We can do that. Okay, then we can, now, once we have that, what can we do? We can make a picture of that. So let's we have, at 0, it's 0, right? Because at 0, the distance it's fallen is 0. Okay, and then at 50, it's, I'm sorry, this is supposed to be t. At 1, it's 50. So let's say this is 50. And at 3, it's 100, right? And at 4, not 4, sorry. At 5, it's 150, right? So that's here. Something, okay? We can do that. All right? And then, we try and figure it out. Okay, now what's the relationship? Right? So we try and fit a curve to these points. So, the curve doesn't look, maybe it's a straight line. Maybe it's not. But it turns out that that's not what the curve will be. That's, I just made those up. The curve is going to look more, well, before I answer that, would it make sense to get this? Would it make sense to get this? 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Would this make sense? 10, 20, 30, 40, 50. So that would mean, does that conform to what you think is really going to happen? Does that conform to your intuition about how things fall? So what I mean is, after 1 second, it's gone 10 meters. Okay, after 2 seconds, it's gone 20 meters. After 3 seconds, it's gone 30 meters. 4 seconds, what's wrong with that? There could be many things wrong with it, but one thing that should go against your intuition is, if this is the case, then what is if we think about the same thing, delta y over delta x, the average rate of change, and what is that, how do we interpret this in this problem? Because now it's not just an x and a y, but these x and y's have a specific meaning. Actually, I should write delta s over delta t. So it's not just like any x and y in math. These have an actual, we're giving them meaning, like a physical meaning. What is this? So what does this mean? We know what s is, we know what t is. What is the change in s over the change in t? That has a meaning. Yeah. What? Yeah, speed or velocity, right? Velocity, right? The change, how do we measure how fast a car is going? What do you say? I think, does everybody use miles per hour? Or do they use meters per whatever it is, okay? Let's say I'm just used to miles per hour, mph. So that means what? That means the change in the number of miles was a change in the distance over a change in time, right? That's velocity, right? So that is velocity. So this is velocity. Okay, so when we talk about the average rate of change, when we're specifically talking about time and distance, then average rate of change means average velocity, right? So now, how does this jar with your intuition? What's the average rate? What's the average velocity or the average rate of change between 1 and 2 seconds? So that's 20 minus 10 over 2 minus 1. That's 10. What's the average rate of change between 2 and 3? 10. What's the average rate of change between 3 and 4? 10. Does that make sense? Do you think things fall like that? Do you think the speed is always the same when you drop something? No, obviously we know that when you drop something, the speed increases over time, right? Everybody has that intuition, I'm sure, right? So this wouldn't work. This would not be how it turned out, right? That would not be how it would turn out, right? We wouldn't get data like this. Right? That would be very weird if we got that data. Right? Something would be wrong. Okay? So actually, I don't know how I drew this picture, and I just made up this data anyway, but this picture somehow looks like a straight line, but that's not the way it's going to be, because that would suggest that the slope here, this remember the speed, or the velocity, is the same thing as the average rate of change, right? So the slope here, meaning the velocity here, is the same as the velocity from here to here, is the same as the velocity from here to here, and so that doesn't make sense though. So it can't be a straight line, it should not be a straight line, right? It shouldn't be a straight line, something wrong if it turned out to be a straight line. So what is the relationship? So that's, we want to figure that out if we were Newton. Okay? So an approximation to the answer is something like this. S equals 10. It should not be like that, because that means a line, right? Right? That would mean the slope is always 10. That would mean the velocity is always 10. Right? Because the slope is the velocity. Right? The slope is the velocity, right? So it should not be like that. But it does turn out to be close to that, which means it's a parabola if you graph it. Okay? So it's some kind of parabola like that. Okay? Okay. So that's the way, that's the real, that's the ball. Right? That's the way it looks. Now, the question that he struggled with was not exactly, I don't know if he struggled with this. Somehow he must have come up with this, or somebody else came up with it first. But then he struggled with, he said, well, what is the speed exactly here? Exactly when t equals 3 seconds. Okay, remember this is time in seconds.